my last device to check here. All right, that's going to be good. All right, so this is the first of 2 lectures on deep learning. The first lecture is today. The second one is a week from today on Tuesday. There's no class on Thursday. So I'm traveling. You guys get a Thursday off, sort of, except for homeworks and things like that. So let me start off with a little story. So when I was a young man, like an undergraduate, everybody studying computer science at Duke had to take a course in assembly language programming. And some of us thought it was kind of a stupid idea, including me. I remember, so this was before you had internet in classrooms and stuff like that. So me and a buddy of mine would sit in the back, and we'd pass a Rubik's Cube back and forth. One of us would shuffle it up in some particular way that gave it a pretty pattern. The other person would sort of unshuffle it. And the rule was you couldn't just sort of use your skills to actually solve it as if you were solving it from scratch. You had to sort of figure out what the guy did and reverse it. So we did that instead of listening to the lectures. And I remember also the lectures, there was a quiz at the end of every lecture. It's kind of the quizzes you have here, except even easier. I remember there was one time toward the end of the semester, and the quizzes didn't count for much, right? But there was one at the end of the semester where Dave and I decided that we would try and answer the quiz without reading the questions, just look at the answers and see which one seemed right. But in a way I was right, in a way I was wrong. So I really haven't used much assembly language, I would say, in the last few decades. But there was a period of time where actually knowing what things were going to be compiled to and how assembly language worked, helped me write much better code. So this is sort of an example of a level of detail that is important for a period of time, and then sort of at some point it stops being important. So what we're leading up to here is next week's assignment. So a lot of people now use neural networks. And most people use them through tools like Torch or Theano. And what I'm going to try and do is I'm going to try and do an assignment which basically sort of opens those things up and looks a little bit under the hood at what those tools do and how they actually work. And this is because, just as I felt it was important to kind of teach people, what's kind of going under the hood, at the level of, Hadoop and the Hadoop file system, and not just focus on high-level abstractions like these data flow languages like Pig. I think it's actually important to know what's going on under the hood in these neural net building tools. So this is kind of a new thing for me. We haven't done this assignment before. So some of this is just kind of, actually today's lecture is mostly kind of standard background on neural networks. So it could be kind of recovering a lot of old ground. Next week, I'm going to talk about the automatic differentiation methods, and I'll talk about how you can use those to build neural networks that have kind of quite complex architecture fairly easily. So this is basically kind of a standard introduction to deep networks. So I'm assuming that people have seen some of this in the past. How many people have seen a intro lecture on neural networks in 601 or someplace like that in the past? Okay. How many people have sort of seen something that sort of specifically looks at deep neural networks? Yeah, okay. All right. So this may be a little bit of review. If you want to get more detail, there are a couple of things I'd recommend. There's a book that's coming out by Yoshua Bengio. So you can get kind of a preprint of this version online. I think it may actually be out now, but you can still get the online version and just sort of read it for free. There's another book which is has a lot less detail, but has some very nice features. It's at a sort of very accessible introductory level. It has a lot of example Python code. So this is an online book that I also kind of recommend. I'm going to be taking some of the description from that. So let me briefly give you a history. So neural networks is kind of weird. It kind of goes in and out of fashion. So I hear it was kind of in fashion in the 50s and 60s, and then I hear that in the late 60s, Minsky and Papert wrote a book which basically pointed out that the algorithm that many people were using, which is the perceptron algorithm that we all know, actually has fundamental limitations because there are lots of things you can't, there are lots of things you cannot compute with a linear function, a linear separator. So that actually caused people to back away from the neural networks techniques at the time. And there was like a phase of maybe 10 or 15 years where people didn't really look at them too much. And then sometime in the mid-'80s, they sort of started getting hot again. Part of this was the popularity of backprop. Part of it was this great set of books by Rumelhart and McClellan called Parallel Distributed Processing. Some of it were experimental successes. There was a system called NetTalk by Terry Sosnowski, which did a really good job at text-to-speech. But then, sort of toward the middle end of the 90s, people started getting more interested, particularly in the academic community, in other things. So things like decision trees, boosted decision trees, support vector machines, a lot of the kind of basic science behind Bayesian models of learning were coming out then. And there wasn't that much you could say about neural networks. So the research in neural networks sort of plateaued, and not that many people looked at it too much for maybe about 10 years. And then, maybe something around 10 or 15 years ago, the interest sort of started to pick up again. So right now, of course, deep neural networks is a huge thing. It's having a lot of impact in a lot of fields. There are stories like AlphaGo. There are stories like the impact it's had in vision. There's lots of people talking about it. Some people are actually frightened of what's going to happen, that we'll make so much progress in artificial intelligence that machines will take over the world or something like that. I'm not sure that's true. There are definitely bad things that you can do with AI, but I don't think we have to worry too much in the immediate future about being replaced. Maybe I'm just pessimistic. Maybe my AI programs don't work as good as Elon Musk's AI programs. But that's sort of where I am. But there's no question this is like an important hot area. So let's spend a little bit of time talking about it. So the simplest case of a neural network is a classifier. And it's broken into layers. So this is the input layer. This is the output layer. And you might have more than one layer in between called a hidden layer. All right. And each one of these circles is an input, is called a unit. All right. So it's going to take some inputs. It's going to compute some function of those inputs. And that output function is going to get passed on to some other unit. Right. And, the same output can be used by many different, you can point it to many different units to use as output. So the inputs can get reused. More generally, so the kind of simplest case is those units all compute basically the same thing a logistic classifier computes. So they basically look at a weighted sum of their inputs, and then they threshold out with some nonlinear classifier. In general, these units can do anything you like as long as it's a differentiable function. So as long as they do some numeric function that you can differentiate, you can stick it in a neural network, at least in principle. So the simplest case of this, and what neural networks were most of the time in the 1990s, was you had a fixed number of hidden layers, usually not very many, usually one or two. You would define a loss. So the loss of your output layer would be something that tells you how well it matches the data. And the most commonly used loss was actually a quadratic loss. So basically, you'd look at the square difference between what you predicted and what the actual target value was. And the units inside would basically be doing this sort of computation. So it would be taking a weighted sum of the inputs. Then it would be passing it through some sigmoid function to basically sort of do the approximate sign computation, just like we did with logistic regression. And then that would get passed on further down the network. Okay. So this is sort of the simplest kind of system. Now, there were exceptions. There were people that built other systems with different architectures. I guess the most famous one of these is a convolutional neural network, which is kind of designed for vision tasks. Here you'll have many, many different layers, but they're all constrained. So each one is basically looking at inputs from a particular local area of the retina or some particular area of the kind of hidden unit that's extracted from that. So the results for these were actually really good. So experimentally, these things were very successful, but they were hard to train. So this picture is from 1998, so it's something that's been around for a while. And here are some numbers from 1998. These numbers here are for convolutional neural networks, and you can see they're getting really good results. This is on the old MNIST data, so classifying handwritten digits, 0 through 9. So the error rates are way less than 1%. The downside is that these things would take literally weeks to train. Okay, so you don't get many different tries to train this. If you're like writing a paper every 6 months, you got 3 weeks to train each iteration of your system. You don't have time to do a lot of experimentation. You could get nearly as good performance with things that were much easier to train. So support vector machines, very stable, simple optimization algorithm. You can use a polynomial kernel and get great results for this sort of task. So the consensus was they worked pretty well, but they weren't really worth the effort. If you want to look at what the learning algorithm is for these sorts of things, it actually turns out to be very simple if you have square loss. You basically, to derive the gradient, which you're going to use, so we're going to optimize this with gradient descent. All we need to do is sort of take the gradient of each unit for that to be possible. Then we can use a chain rule. And when you do this, you get a pretty simple formulation. So here's the backprop equations for a multi-layer neural network using square loss and sigmoid logistic units. So essentially what you do is first you do the computation. So you figure out what's the activation level at each point in the neural network. So you're going to compute something which is the error at a particular node. So the error at a particular node in the output layer is defined like this. So it's the loss with respect to the target, okay, times this quantity here, all right, which is for a logistic unit. This is high if the activation is sort of around 1.5, around 0.5, and it's low when the activation gets close to 0 or 1. Then you basically take that quantity and you push it back through the hidden layers step by step. So to define the error at a hidden layer, you get this sort of quantity. So this is looking at the error in the next layer, and again doing this sort of scaling. All right. So then at the end of the day, we've got an error quantity at each node, which is essentially the gradient. And you can use this to update all the weights in the network. All right. So that's the basic idea. I'm going to step through this a little bit in a kind of matrix notation, just so we're kind of all on the same page. So you probably have seen something like this before, but pay attention anyway. The notation will be kind of helpful going on. So we've got an input layer, we've got some hidden layers, we've got an output layer. Just to make this concrete for image classification, right, for these MNIST digits, each one of these is an image that's 28 pixels by 28 pixels. So that's 784 pixels. So you'd have an input layer that was very wide, 700 neurons wide. And each of those would be 0 or 1, depending on that pixel was white or black. Then you'd have a hidden layer or maybe several hidden layers. And at the end of the day, you'd have an output. You'd have 1 neuron for each class, 0 to 9. And you would basically predict the class which sort of had the highest activation at the end. Okay, so here's some notation. I'm going to use W super L. L is the layer. So it's, here it's either 1, 2, 3. Okay, so W super L is tells you what layer you're in, and then, I'm sorry about the light show. I don't know what's going on with this. All right, I'll keep you awake, or possibly relax you. I think blue lights are supposed to be relaxing, I'm not sure. And then JK is basically the source and destination in that layer. Okay, so that's going to be our notation. Whoa, let's go back a bit. So we can basically group these things. So W super L is a matrix, and the jkth element of that matrix is the particular weight for that layer. So basically, for every layer, I'm going to have a weight matrix. All right, that encodes these connections. All right. There's also a bias term. So again, for every layer, there's going to be a bias term which gets combined with the weights. What gets produced at the end of the day is an activation. Okay, so the formula we're going to use here is the activation for node J at level L. You apply a sigmoid function to this quantity. So this is basically taking all the weights of things in the previous layer, combining them appropriately, weighting them appropriately, so we get our weighted sum. Then we get a bias term for that vertex, for that unit. And then we apply the logistic function. So sigma here is the logistic function. We can also write this as a matrix computation, right? So I'm going to use A super L for a vector of the activations at level L. So A super 2 will basically be the outputs of each of these neurons. All right. Okay, and the way we compute it is we basically take A super L minus 1, we multiply it by the weight matrix, then we add the bias matrix, and then we apply the sigma function, and this is component-wise. So this is a vector input, a vector output, and how do we define this function on vectors? It basically just applies the sigma to every component of that vector. Okay, so one more notation. Sometimes it's useful to look at Z. So Z is the output of this linear classifier before you run the logistics. So it's just the weighted sum plus the bias. Okay, so the computation you do once you've got the thing trained is very simple. You basically go layer by layer forward. All right, so that's feed forward. That's why it's called a feed forward network. So for each one, you basically, well, the inputs are kind of given to you, right? And then we're going to basically look at this computation, this matrix computation, and we're going to use it to compute the first hidden layer, then the second hidden layer, and finally the output layer. Okay, so it's just a loop. All right. So now let's talk a little bit about learning. So again, what we need to do is we need to define a loss function. Okay, so this is all following that online book by Michael Nielsen. So the cost function here is the notation is C. Okay, so C underscore X is the loss at example X. So the loss function for the whole network is just the average loss at each example. The loss function we're going to look at here is square loss. So it's the activation at the output minus the target activation. Okay, and then this is all squared. So this is what we'd end up with for our loss function. Okay, so here's another bit of notation here. We've got our output vector. So Y is the target output. So X and Y together need to let you define the loss at an example, obviously. Okay. So now to give you the equations for the backpropagation, which, again, this is going pretty fast, but you've probably seen this before. What we're going to do is we're going to basically look at a particular neuron here, and this picture is taken from Nielsen's book. So his mental image is there's some daemon there that's going to be adjusting the behavior of that neuron in some way that's helpful for lowering the loss function. Okay, so the signal that little daemon is going to have is called delta. So we've got delta, and it's the index of a node at a level, and this superscript is the level number, okay? So what is that? So we're just going to define this to basically be the derivative of the cost function with respect to z, which is the output at that neuron before you do the sigma. So that basically makes things very clean mathematically, okay? So if we look at the backprop for the last layer, what you basically want to do is you want to get the gradient of the cost function. So how do you do that? So what we're going to do is, and this is for one example. All right, we're going to look at the gradient of the cost function. We'll just use the chain rule. So it's the gradient of the activation, the cost function with respect to the activation times the gradient of the activation, right? And the gradient, we're actually going to look at, actually this should be, yeah, the gradient of the activation, and the activation is just sigma times the z at that point. So we can look at the derivative of sigma, okay? So if we want to write this in, again, in vector notation, then this will be a vector for the nth level. This is another vector. So this whole notation here is one vector, and the components are basically these guys, right? So they're the gradients of c with respect to this activation. And these are the components of z, the unthresholded, pre-sigma activation, and then we apply the gradient of the sigma function here. All right. So this is the formula we use for the last level. So for the particular case of square loss, then this guy right here has a very simple form. It's just, well, I guess there's 1/2 in there somewhere, or we have to modify the loss, so we've got a factor of 2. But it's basically the activation minus the target value, okay? And here we're basically taking ZL, we're applying the sigma prime to it, and then computing the component-wise product. So this is component-wise product, which is sometimes called Hadamard product. Okay. So this is for the final level layer. All right. The formula for the previous layers is actually very simple, and so you can basically compute the this delta term for every previous layer. Okay, and it has exactly the same meaning. Okay, it's the gradient of C with respect to the activation at that previous layer. Okay, basically what we do is we take the previous, the next output, the next loss function. All right, we multiply it by the matrix, the weight matrix. But since we're kind of pushing things backward, we multiply by the inverse of the transpose of the matrix, because we're going backwards. All right, and then again, we have the same sort of quantity that we add at the end. All right, so once I've computed these for level, capital L minus 1, and then capital L minus 2, and all the way back to the beginning, then I can actually compute the weight updates. Okay, and again, the formula for these are pretty simple. So the gradient that I want for the cost with respect to each bias term is just the loss function at that particular neuron, that unit. Okay, so that's at neuron J in that level. All right, and the gradient I have for the weight is defined by this. So it's the activation at the previous level, and then the loss at the next level, and this is for the output, and this is for the input. All right, so one way of thinking about this is the activation at the input times the loss at the output. Okay, so at the end of the day, we basically have these formulas. Okay, these are all basically very simple formulas, we can define them easily as a set of matrix and vector operations. Okay, so there's a little bit of matrix multiplication, mostly vector operations. So there's a very sort of succinct description of these things if we're using a package which lets us write matrix operations. So we had to be careful how we did this, right? So so part of this is part of the cleanness of this formalism is we're basically giving a different set of indices for the weights in each layer and the activations and so on in each layer. So I can think of these as matrices. But it's a nice, clean description of what's going on. And again, what the computation is, you have to apply these operations backwards. So first we go forwards like we did before, so we figure out what the activation is. And then once I've done that, I'm going to figure out what these error terms are, these deltas, going backwards, starting from the output layer, then going to the previous layer, then the previous layer, and so on. Okay. And then once I've figured out what those deltas are, I can just read off what the weight updates are. Okay. So this is a neural network. We're going to talk about generalizations of this, but just kind of keep this as in your mind as sort of like the prototypical neural network. So a couple of points to make. Why is this interesting? So one reason it's interesting is because it turns out that these sorts of networks are very expressive. So if you have one logistic unit, so you're basically taking a weighted sum of things and thresholding it, one thing you can easily do is you can set the weights low enough so essentially all those inputs have to be active to pass the threshold. So you can use it to implement an AND of several things. Or you can set the weights high enough so if any of the inputs is active, then you're over threshold, in which case you're implementing an OR. Okay? So you can implement a function which is the AND of a bunch of things, and you can implement a function which is the OR of a bunch of things. So if you have ANDs and ORs, and I guess you can also implement a NOT, right? If you have ANDs and ORs, then you can implement any Boolean function. And in fact, you can put any Boolean function in a sort of canonical form where you basically have the OR of a bunch of ANDs, all right? In which case, you just need one hidden layer, and that will let you compute any Boolean function. The downside of that is it might be a really, really wide hidden layer. So to give you an example of a case where you can do this, but it still doesn't work out real well, the parity function. The parity function is computed, you get a set of n bits, and it's 1 if there's an even number, it's 1 if there's an odd number of bits set to 1, and it's 0 if there's an even number of bits set to 1. Okay? So that's what parity is. You can think of it as an extension to XOR. All right? And you can write this in a Boolean function that's just an OR of ANDs. And you can therefore encode it in a single neural network with one hidden layer. But it turns out to be kind of expensive to do. So basically what this is if we're just looking at 4 inputs, right, then the different cases, so every bit matters, right? So in each one of these ANDs, you've got to consider all the configurations of these bits. There are basically 2 possibilities. Either you have exactly 1 thing turned on, or you have exactly 3 things turned on in this case. So you can list all the things where there's 1 thing turned on. Okay, so there are 4 of those. And you can list all the things where there's 3 things turned on. Okay, and again, there's actually only 4 of those, right? So in this case, we'll get something like 8 terms in this Boolean function. But in general, as this gets large, this computation gets pretty hairy. So if I had 32 inputs, for example, then I've got to consider having 1 bit set, 3, 5, 7, 9, 11, so on bit set. Okay? And when I'm looking at, say, all the patterns where exactly 13 bits are set, then I'm looking at 32 choose 13 different patterns. Okay? So in general, you end up with exponentially many an OR of exponentially many different AND terms. So this is, it's expressive, but it's also limited in some sense, because if you're limiting the size of the hidden layer, then there's some things you can't compute easily. So one way you can make things more expressive is to make, is to basically add hidden layers to your neural network. All right. So, so here's a different way of doing parity. Okay. So I know that I can actually just do XOR. So that basically means exactly one of two inputs is set using a two-layer network. All right. It looks like this. I've got my two inputs. I've got one that computes OR. I've got one that computes not AND. And then I've got one that computes AND here. And then I'm done. So you can check that later if you want. But you can do this with, you know, just kind of fixed size computation. All right. And then if I want to do parity over n inputs, I can basically do a big tree of these things. So I take this thing and I put it here. Okay. So that computes the parity of inputs 1 and 2. Then I have something that computes the parity of 3 and 4, and so on and so forth. And so now I know that there's exactly one of these things set or not, right? I can look at those two and I can compute parity of those two inputs, all right? And that will tell me how many things, you know, either there's, this is on and this is on, in which case it's an even number, right? And so on and so forth. So you can basically do this parity recursively as long as you can build a tree of depth log n, okay? So now I've gone from exponentially many hidden nodes to just a polynomial number, something like n log n. And what I've traded off is I have a deeper computation, all right? And there's also an intuition why this would be useful. So essentially, what's going on here is you're doing a computation that's going to get reused multiple places. And in general, you can imagine building a deep network and maybe combination with reusing parameters in multiple places in the network, which is called parameter tying. You can use this to implement subroutines. So you can imagine, let's say you're like writing code for face recognition. If you're doing this, you might start off with a whole bunch of subroutines, like, you know, can I see an eye somewhere in the top left, and then another eye in the top right. So those are like two different subroutines. You're calling them in different places in the network, right? And then each of those might actually have some subroutines that get called. So, you know, do you see something that looks like an eyebrow? You know, do you see something that looks like the iris of an eye? And then each of those might have further subroutines, all right? So in a deep network, you have something like subroutines. So this gives you the ability to write more complex, more compact programs. That's essentially the idea. So that's one reason these neural networks are interesting, is because you can express a lot of things with it, all right? The other reason they're interesting is because, I'm not going to say they're easy to learn, but you sort of know what to do, okay? So the learning algorithms for these are pretty general. So if you have a network where all the units are differentiable, you can use gradient descent. All right, so we'll talk a little bit about the scalability of this, but it turns out it's pretty scalable, okay? And it also, it's applicable to many different types of computational units. In practice, it doesn't always work well for certain types of computational units, but it does work pretty well for a lot of different kinds of networks and architectures. And over the last 10 years or so, we're getting a lot of experience as to what kind of architectures it will work well for. So we're starting off and we have a pretty good learning algorithm. Now, as you guys know from the SGD assignment, dealing with gradient descent algorithms can be a little bit tricky. So they tend to have parameters, and parameters need to be tuned. So things can get kind of tricky. So we'll come back to that in a second. But this is another reason why neural networks are popular. You know, it's like learn it, gradient descent. It's a very kind of reusable strategy. All right. So let's talk a little bit about computational properties. So in the 1990s, computers were slow. That's part of why it took 3 weeks to train things. But it was also the case that in the 1990s, you had to train neural networks with basically conventional computers that perform one operation at a time. So there's some tricks we can do now, all right? So the way neural networks are trained is usually with some variation of stochastic gradient descent. All right. So we've talked about this. You take either one example or maybe a mini batch of examples. You compute the gradient on that batch of examples. Okay. You update your parameters, and then you move on. So this is the way we train neural networks almost all the time. You keep the model in memory, so there's a limit on how big the model can be. But the data can be very large because you're just sweeping over it. So it's not as fast as if you were going through the data set in parallel, but it's pretty workable for pretty large data sets if your model parameters don't get too large for memory. So this is a scalable algorithm. It's a streaming algorithm. You might have a long training time, but you can still approach large data sets if you're kind of patient. And actually, there is some ways of using parallelism just in this simple, well-understood streaming SGD sort of framework. So to explain this, let me just go back to our formulas here. Okay. So when we're doing logistic regression, okay, which is basically sort of the thing that happens in a neural network, okay, most of the time, or something often, right? So what's the computation that we're doing? So on one example, what we're doing is we're computing the inner product here of x and w. Then we're doing a function on that. Okay, so first we compute the inner product. So basically every neural network architecture that I've ever heard of has a lot of inner product computations. They get done over and over again. You're looking at different combinations of weighted features and doing something with them. So there may be some chance of doing this in parallel. If we think about what that inner product looks like, right, it's a big sum of products, right? So maybe you can do those in parallel somehow. But there's some other tricks we can do. So the inner product looks like this, right? So we could do all these things in parallel, right? But it turns out we can do a little bit more. In a neural network like this, okay, we'll be computing, this actually should be z here, the dot product of x and w, ignoring the bias term right here. Okay, but we're computing this dot product. Okay, this is this is doing dot product for a particular example and a particular weight matrix. Okay, all right. So we could also write this as a vector by basically saying we're going to take x, the example, right, or our inputs times w, right. So that's the weighted sum. Okay, this is a way we can write this inner product computation as well. Okay, and it might be kind of helpful to kind of look at this. So these are the weights that take you from input xi to xj, right? So what I've got here is I've got basically all the activations at a particular layer, all right, and I'm bundling them together. So I get all the activations at that layer as a matrix product, a vector matrix product, x times w. All right. But we can actually do a little bit more than that. So supposing I have a set of, let's say, k examples. So maybe I've got 100 examples. Okay. It turns out, so these are my examples. All right. I'm going to take these and I'm going to multiply these by the weight matrix. All right, so if I take these x's and put them in a matrix where each row of the matrix is one example, all right, then of course each row of the matrix x times w is going to have the inner product of one of these x's with one of these w's, right? So the first row is going to be all the inner products which correspond to all the z's for the first example. This is going to be all the inner products corresponding to all the z's for the kth example, right? So each one of these rows corresponds to computations on an example. Each one of these columns corresponds to the output for a particular unit in that layer. Okay, so this is a matrix multiplication, and in matrix multiplication there are even more chances to do things in parallel. Okay, and the nice thing is matrix multiplication, since it's something that gets used over and over and over again in many different settings, It's something you can tune. You can work really carefully as to how to parallelize it. You can build hardware that does that computation in parallel. And that's what we do, okay? So, so if you're using a modern matrix multiplication library, so the ones that are used that back up MATLAB or the ones in NumPy, they do these matrix operations very fast. If you're working on a multi-threaded machine, you can do them in parallel with a little bit of configuration. And a lot of implementations will exploit that parallelism automatically without you doing anything. Well, not quite anything. When you write your code, you've got to use matrices as much as you can, right? So that's one way to get parallelism. And the other way to get parallelism is looking at special hardware. So how many people predict what are the most important 3 letters on the next slide? Anyone have a guess? All right, yeah, okay, good. So GPUs are basically designed to do matrix operations really fast, all right, in parallel. So they work on dense matrices. Some of the stuff we were talking about in this class is on sparse matrices. GPUs are, designed for dense matrices. But this is a very common way of training. So basically what you'll do is you will arrange things so that your matrix multiplications and similar sorts of math gets done on GPUs. You'll group them into mini batches. So mini batch size of, say, 128 or 256 would be pretty common. And that basically lets you do a bunch of examples in parallel. It doesn't make the learning algorithm better, typically, than a smaller mini batch size, but it will make your algorithm run faster. So you can do more experiments and more tuning and so on and so forth. Again, most of the back-end packages, the systems for dealing with neural networks can exploit this. It's non-trivial to sort of figure out how to talk to your GPU and get it to do your bidding, but it's possible and it's been done. So GPUs are not super expensive. So you can get a really nice GPU for neural network processing for like $500. This is actually a little bit old, but a GPU with 12 gigabytes of memory, which can hold maybe a few million parameters, is sort of what you'd kind of get for that. All right, and you get at least an order of magnitude speed up. So 20 to 50 times is kind of what's commonly reported. So this is how you do parallelism with neural networks most of the time. So it's kind of hidden from you, but it's there, and it's important because it makes things a lot faster. So the next level up would be to build systems that do the kind of parallel processing that we've been talking about with the perceptron paper on iterative parameter mixing, and we'll talk about other techniques later in the class. But so these are things where you're basically distributing a really, really large computation against the whole cluster. All right. So there are ways to do that. They're not as widely used in the neural network community. Okay. There are basically 2 things you can do. One thing you can do is partition the data. So you do something where you train on some subset of the data on one GPU and another subset of the data on a second GPU. Then you have to combine the parameters somehow because the parameters live on each GPU. So you can do that by partitioning the data, in which case you're usually doing some form of this iterative parameter mixing strategy. The other thing you can do, which whether it's possible or not depends a lot on the architecture of your model, but it's often possible to partition the model across different GPUs. So you could, for example, a really easy case is supposing you have a model where you're basically running 2 neural networks side by side and just combining the outputs at the end, right? And obviously you can do sort of training for those neural networks to some extent, at least in parallel. But there are other things that you can do. So it's common, for example, to train some layers on one GPU and other layers on another GPU. So you're sending gradients back and forth between the GPUs, but you're keeping 12 gigabytes of parameters in one GPU and another 12 somewhere else. So that gives you more space for parameters. I don't know a whole lot about these things. This is often needed when you're training really big networks. It's not easy to do. There are not a lot of really good tools for doing that out there now, as far as I know. Okay, so this is all pretty simple, right? You guys are all experts in neural networks, all right? So now that I've told you what it's all about, it's, you know, your like salary has just tripled, right? You know, it's like jobs at Facebook, just pick me up, let's go, right? So in fact, people that are good at training these things are very much in demand, but they're in demand because it's, even given this machinery, it's kind of hard to train them. And I'm going to talk a little bit about some of the reasons why this is hard, okay? So let's just look at these updates right here, okay? So this is very computationally simple, okay? We've got an error at this point, all right, the output layer, and we're taking it and we're basically pushing it back one level. To do that, we're doing, you know, this combination, which basically just involves, you know, a matrix multiplication. So it's a linear kind of thing, but then we're also multiplying it by this quantity, okay? The activation times 1 minus the activation, all right? So let's just look at kind of like what would happen along one path. So let's look at a deep neural network, and we've got our cost at the end, and we've got a set of things that sort of get by. Let's say these are all, you know, some parameter, bias terms or whatever. But let's figure out what happens to this quantity as it kind of goes backwards through this network, all right? So the key thing that happens is we're multiplying it multiple times by something that looks like this, all right? That's the activation times 1 minus the activation. That will look like this, okay? This is what the derivative of the sigmoid function is, okay? Like I said, it gets very small when you have low activations or high activations, all right? Because if you think about the sigmoid curve, it sort of flattens out as you get to high negative or high positive numbers. And its highest sort of right around 0, okay? The actual value of the max is at 1/4, so the max for that function is 1/4, all right? So you're basically taking this error signal you get at the output, and you're multiplying it by something that's smaller than 1/4 here and smaller than 1/4 here and so on, all right? So this is actually not good, all right? So this is not a numerically wise thing to do. So as you go deeper and deeper in this network, right, the error signal you're getting is going to get smaller and smaller, okay? So if these activation sigmoids are less than 1, which is often the case, then we're multiplying by a whole bunch of numbers less than 1. So if we get a few levels back, the gradient's going to start to get really, really small, okay? So this is called the vanishing gradient problem. There's another problem which is a little bit less common. So it might be that you can sort of change things so that the, you know, typical multiplication factor isn't 1/4. Maybe you can make it a little bit bigger, right? So what if you can push it up to like 0.5, then things will get slower, small more slowly. Or maybe you can push up to 0.75, or maybe you can push up to like 1.5 or 2. Well, that's not so good either, right? Because if we start multiplying things by a bunch of large numbers, then we get exponential growth as we go back, right? So then we'll get gradients that are really, really big. And that's also a problem, okay? That's called the exploding gradient problem. It doesn't happen quite as often, but it can happen in certain network architectures. And again, it's a big problem. You get huge gradients, and then in your learning step, you'll make really big steps through parameter space, and you'll often, you know, run into problems with the optimizer when you do that. So this is one of the difficulties. If you want a kind of a long description, a long analysis of these difficulties, one paper I recommend, this is from a couple years back, Yashua Bengio and Xavier Glorot. So this is a paper where they looked kind of very systematically at what these problems were on some natural data sets and also some artificial data sets. So here's one example, all right? So here they're looking at what the gradients look like in a neural network. So these are the gradients, the deltas basically, at layer 1, all right? That's the one closest to the output. And then layer 2, and then layer 3, and layer 4, and layer 5. right? So you can sort of see the vanishing gradient right here. So when you get to things at layer 5, the gradients are really small, and the parameters are going to change very slowly. All right? And here are some graphs they have. So these top two, this black line and this blue line, yeah, there's a black line up there. I don't know if you can see it. There's a black line right here. All right, this is at a test error of 85%. Okay, so this is basically our kind of standard 1990s neural network with 5 hidden layers. All right, as you train it for 25 million examples, this is a synthetic example where they can generate as much data as but it's a hard one. And you can see not a lot is happening here. It's just dead stuck. All right. So 4 levels, okay, then you, after training on more than 500,000 examples, you start to see some behavior changing. All right. Okay. So basically 4 levels, it's possible to train, but it's training pretty darn slowly. Okay. 5 levels is just, you're just dead in the water. Nothing's happening, okay? So one of the problems here is that the gradients get small, but there's another problem which is associated with the sigmoid units, okay? So these sigmoid units, if you look at them, the gradient gets very small at the tails, right? They approach these constant functions when you get to the end. All right, so that basically means if you have a neuron where the activation has kind of gotten up to like +6 or -6, so the z's, the weight before you do the threshold, that basically means for all practical purposes your gradient is going to be 0. So that is never going to change its behavior. Those parameters are just not going to change. All right, the unit basically gets stuck where it is. Okay, so how likely is that to happen? All right, well, I mean, it depends on how big your network is, okay? So for the digits, we had 784 inputs. So let's say we start off connecting all the inputs to the nodes in a hidden layer. We've got a bunch of things in the hidden layer. So each thing in the hidden layer has 700 inputs. And let's say we randomly give these things weights, I don't know, between, +1 and -1, okay? So almost all of those neurons in the first hidden layer are going to be stuck. You're summing up 700 numbers that are between +1 and -1. So what you're looking at is you're looking at the standard deviation of a big, big sum. All right. So if you've got 500 units, this is, I guess, normal between 0 and 1, right? So you've got 500 units. The standard deviation is about 22. Okay, so your chance of getting a neuron that's not stuck is really, really low. Okay, and this is also a problem with neural networks. Okay, and the paper has some nice visualizations of this. So this is actually using not just initializing between 0 and 1, but a really carefully chosen initialization scheme. And you still see sort of behavior kind of like this. So this is the average activation at one layer. This is layer 3, okay? And these lines are the standard deviation, so it sort of gives you an idea of how much variation there is. All right, and this is a 4-level network. So that's the one that, if you recall, basically didn't do anything for, 750,000 examples, then finally start to break down and start training, okay? So here's what's happening to it, okay? What's happening to it is the deep layers, okay, are basically not changing very much at all right, until you get to maybe 100 passes over the data. And then they sort of finally start getting unstuck, all right. No, I take this back. This is the, layer 1 is the one closest to the input. Layer 4 is the one that's closest to the output. Again, so it's easy for units to get in this mode where they're not very responsive. And then basically training is excruciatingly slow. All right. And again, you can sort of see like there's this regime, okay, where the weights of things are not changing very much at all until they finally kind of break loose at this point. All right. So, You know, here the bottom layer is still stuck after 100 epochs.